Bismillahirrahmanirrahim. Today is 6th of July 2020. It's an alternative lecture to the one that we missed due to unforeseen circumstances on Friday. So our makeup class is there. So if you remember from the previous lecture, we discussed the application to look into physical phenomena, to look into practical demonstration from our daily life. And you have seen quite a few interesting applications from our daily life. Today we will extend our journey. We will try to make some more modeling, in particular closely resembled, closely effective, more effective in electrical engineering, the modeling of electric circuits. Today's lecture is more vital, more interesting for the people of this technology because they are directly connected with them. Modeling is a demanding, is a challenging task for everybody because you look into the physical phenomena that exist in reality, make a mathematical model, and we see that the mathematical modeling of every engineering problem will turn out to be differential equation. So as an application, as an important application of differential equation, we will try to model electric circuits. And since you are the student of this technology, electrical engineering, so I believe that you are having better understanding about this topic in comparison of me, because you more look into the practical demonstration in the lab, perform experiments over there. So we will try to take a glimpse of idea how the mathematical formulation is there if you try to model certain electric circuit, RL circuit, RC circuit, RLC circuit, for example. What type of the equation will be there? And once the model is there, how do we look into the solution? I believe that based upon the previous lectures that we have conducted so far, we should be able to look into the solution of certain type of the first order as well as higher order differential equation. So inside the first order differential equations, we have quite a few techniques available. We started off with the basic one, variable separable form, homogeneous, non-homogeneous of first order, exact, reducible to exact form, a linear first order differential equation, the one which can be reduced into the linear first order known as Bernoulli's, and stuff like that. Into the higher order differential equation, any order greater than 1 is assumed to be higher order. So pretty much on the same line, we say that even second order differential equation will be considered as higher order differential equation. We will be having homogeneous, non-homogeneous inside the higher order differential equations. Much easier if we look into the homogeneous part. And then, based upon the nature of the root, we look into the general solution of the corresponding homogeneous equation. If the equation is non-homogeneous, the right-hand side f of x is non-zero. So we have discussed two vital techniques available in the literature: the method of undetermined coefficients and the method of variation of parameters. Sometimes we feel more convenient to look into the implementation of method of undetermined coefficients if the right-hand side is a polynomial of certain degree, exponential function, or simple trigonometric functions are there. But if things are more complicated to the right-hand side, as an example, product of exponential and trigonometric function, so then you're better off to switch on to the technique known as method of variation of parameters. So when the equation is non-homogeneous higher order, so we will have to find two solutions: complementary function, the solution corresponding to the homogeneous part, and one more, particular integral. By considering non-zero, and then the combination of them will take us to the general solution of the given non-homogeneous higher order differential equation. So keep an eye on all those aspects. We will try to look into the modeling of some simple electric circuits behind the scene. Designing good models is of course a demanding task. The computer can't do. You have to do. So therefore, setting up models has become an important task in modern applied mathematics. The best way to gain experience in successful modeling is to carefully examine the modeling process in various fields and applications. Accordingly, modeling electric circuits will definitely be profitable to all the students, in particular for electrical engineers, and that's what we are looking for. The simplest electric circuit is a series circuit, so it is going to be connected. Series, we know the difference. I mean, general speaking, or in the news term, we know the difference between sequence and series. So they're all being connected one another. All the components, all the elements to be connected one another. It's a series circuit in which there is a source of electric energy supplying an electromotive force. So electromotive force is there. We see physically as an example of a battery or a generator. So these are the source of energy behind the scene. Then another component, a resistor, which uses that energy. For example, an electric bulb. So electric light bulb, what kind of circuit is there? We will try to sketch the circuit today. I'm not good at drawing, but anyway, we will try to look into use whiteboard. So take a note to the figure that we are trying to draw of a very basic electric circuit. Yep. So let's take start. What are the elements that we need to keep an eye? So exclude that you can try yourself, but it's better if you give me chance. Excuse me, if you give me a chance. Behave yourself, man. Take a note. I will try. Stop doing that, man. You're in the class. Behave yourself.
Sir, you can use Microsoft Paint if you want. Here you will face some troubles with the students.
But you should. I mean, the people should behave themselves. They're mature enough. Okay, then we move on in this way. The rest of the part is to be done by you people. I give you an idea. Anyway. When we look into the simplest electric circuit, so there will be a resistor, the resistance of a resistor, the current I will be there. We will have to use switch, of course, turn the bulb on and off. And then, of course, the source is there, positive with positive and negative charge. So if you close the switch, a current I will flow through the resistor, and this will cause a voltage drop. That is the electric potential at two ends of the resistor will be different. This potential difference or potential drop or voltage drop can be varied by an instrument known as voltmeter. If you look into the basic elements of a series circuit, so that series circuit will consist of a resistor and connected, and the form of the series basically stand for voltage. Some people also prefer to utilize capital V. So because it depends upon time, the voltage is going to vary with respect to t. So this is all. E is going to be function of t. So we look into the definitions first, and then the developed formulation behind the scene. A resistor is an electrical component that limits or regulates the flow of electric current in an electric circuit. The measure of the extent to which a resistor resists with the flow of current through it is called as resistance. As a symbolic representation for resistance of a resistor, we will utilize capital R, stands for resistance of a resistor. What we see from experiments that there will be a law behind the scene. States that, and is also valid, the voltage drop across a resistor is proportional to the instantaneous current. So make them directly proportional to each other, and then get rid of the proportionality by introducing a constant of proportionality. So eventually we will be having an equation E is equal to Ri. Capital E stands for voltage or electromotive force. Capital I stands for current, and then R, the constant of proportionality, is called the resistance of the resistor. If you look into the units, the current is measured in amperes, the resistance capital R in ohms, and the voltage in volts. So besides resistor, we have two important elements being utilized in more complicated circuits known as inductors and capacitors. What is an inductor? An inductor is a passive electric component that stores energy in the form of magnetic field. In its simplest form, so it consists of a wire loop or coil wound on some suitable material. Basically, an inductor opposes a change in the current, having an inertia effect in electricity similar to that of mass in mechanics. Whenever current through an inductor changes, that is, increases or decreases, a counter electromotive force, EMF, is induced in it, which tends to oppose this change. So if you assume that capital I stands for the current, then the time rate of change of current is going to be described by di upon dt. Capital I stands for current. Since it is going to be function of t, so the time rate of change of current is going to be di upon dt. This produces a change, a counter electromotive force. Then E is directly proportional to the instantaneous time rate of change of the current. That is, E is directly proportional to the time rate of change of current, di upon dt. Get rid of this proportionality sign by introducing a constant of proportionality. So E would be equal to L di upon dt. Now, where the constant of proportionality L is called inductance of the inductor. The units are going to be Henry, denoted by capital H. The units of time is going to be seconds. Now, with the passage of time, we are going to talk about mathematical formulation. For resistor, we will be having Ohm's law, capital E equal to capital R I. The constant of proportionality in this case, capital R, is called resistance of the resistor. Over here, capital E is equal to L di upon dt. L is called the inductance of the inductor. Capacitor, I believe that you must have gone through all these things. Anyway, we are just recalling basic concepts. A capacitor is a passive electromotive component of an electronic circuit that has the ability to store energy and opposes any change of voltage in the current and the circuit. Experiments yield the following law. What the law is, the voltage drop across a capacitor or condenser is directly proportional to the instantaneous. By introducing constant of proportionality C in this case, eventually we will be having an expression for E. We have an expression for resistor describing the resistance for the resistor. In the case of capacitor, we will be having E is equal to 1 upon C times Q, where C is called the capacitance. The current I is defined as the instantaneous time rate of change of the charge Q on dq upon dt. So if capital I is equal to dq upon dt, and we are interested to find an expression for Q, so take integral on both sides with the variable of integration t. So differential to the right hand side. The effect, or they will cancel each other. integral and differential. So Q will be equal to integral of capital I of t with the variable of integration t. So take this expression of Q from here by integrating both sides with respect to t and plug in over here. So once we take an expression of Q from this expression and plug in over here in that equation number 31, so we will be having an expression for capital E equal to 1 upon C times the integral of I of t is going to be integrand. The integral will be performed with variable of integration t. So these are the essential components before we move on with different type of circuits. Another vital law is there because all the circuits, they are based upon this Kirchhoff's voltage law heavily. What the law states, it states that the sum of all the voltage drops, potential drops around any closed loop will be equal to the sum of the voltage rises around that loop. In other words, this law states that the algebraic sum of voltage around the closed loop is going to be 0. You need to combine together all sort of voltage drops, and that must be equal to the voltage rises, electromotive force, capital E being the symbolic representation utilized for voltage or electromotive force. All right, so we look into few examples from different types of circuits. The first one will be an RL circuit. So we have gone through with capital R as a symbolic representation with the units. Let me mute all of them. All right. So take the first one, RL circuit. R is a symbolic representation for resistance of a resistor, as for the inductance of an inductor. So it means that we will be having our resistance and inductance. The units for resistance is ohm, whereas the units for inductance, so it is going to be measured in Henry. And we have, the diagrammatic representation for resistance like a zigzag, and for inductance, different style is there. Small circles are there alongside the straight line. So anyway, take this one and do it yourself. The figure of an electric circuit known as RL circuit. So we have to obtain the current I at any time t in the circuit, assuming the resistance of a resistor and inductance of an inductor to be constant, since we already have gone through with that. If you remember, we have three different kind of expressions for capital E. When we talk about capacitor, When we talk about inductor, second expression is a and. When we talk about a resistor, we will be having another expression for capital E. So to make difference between them, now we are going to utilize different symbolic representations. We know that the voltage drop across the resistor is going to be described by that. E was equal to capital R, capital I. No, we are going to utilize that symbolic representation for E in the case of resistor. ER stands for energy being discussed in the case of resistor. Also, the voltage drop across the inductor, since the symbolic representation is capital L, so we do utilize that symbolic representation capital E, L as a subscript notation. So now we have two different types of voltage drop. By Kirchhoff's voltage law, what the law states, the sum of two voltage drops must be equal to the electromotive force, the source, the main source behind the scene. That source could be a battery, that source could be a generator or whatever, you name it. So then you need to combine them. ER plus EL must be equal to capital E, the electromotive force. What is ER? Capital RI. What is EL? L di upon dt. So this could also be written as, since L and R are assumed to be constants, so we can divide this whole expression by capital L. So capital R upon L is equal to capital E upon L. So finally, we will be having a sort of differential equation. In the case of RL circuit, so if you carefully look into this one, it is known as first order linear differential equation in the dependent variable capital I, R and L are constants. So it's a linear differential equation in the dependent variable capital I, and we know that. How do we simplify this one? If you go back to the previous lectures, for the first order linear differential equation, we will have to find the integrating factor. By obtaining the integrating factor, we go into multiply the equation by that integrating factor, and the resultant is going to be integrated. Eventually, we find the solution of the linear differential equation. So these are the highlights. How do we look into the form of the linear equation? To get the solution, we need to find the integrating factor, and then with the procedure behind the scene, we get down with the general solution of this type of the differential equation. So anyway, this is going to be the very first mathematical model. How we come down with the mathematical model? It's RL circuit. We will be having resistor, we will be having inductor. Based upon the voltage drop across the resistor and inductor, we utilize Kirchhoff's voltage law combined together, and that will be equal to the electromotive force. So the combination of voltage drop, sum of all sort of voltage drops must be equal to the electromotive force. So combined together, and from simple manipulation, we can get down with the most precise form of the differential equation. So this is the mathematical model. If you are going to look into the RL circuit, the corresponding differential equation will be linear. Linear first order, because if you try to look into the linear and non-linear discussion, it is going to be different when we talk about higher order differential equation. So over here, we are going to talk about the first order. Pretty much on the same line, we can look into RC circuit. The previous one was RL. Resistor was there. the inductor was there. No, instead of inductor, we are having capacitor. An RC circuit is a circuit that contains a resistance, capital R, resistance of a resistor, and the capacitance of a capacitor. Is there? So in an RC circuit, we will be having a resistor and a capacitor, and of course, the electromotive force. So if you are interested to find the current at any time t in the circuit, assuming capital R and capital C to be, again follow those criterion. The voltage drop across the resistor is going to be described by this equation, and the voltage drop across the capacitor is going to be described by that equation. So we have a resistor, voltage drop across the resistor. The very first equation is there, and then the last one. As a symbolic representation, EC, to make different symbolic representation from the E being utilized for resistor, EC in the case of capacitor. And then we utilize Kirchhoff's law, states that the sum of two voltage drops must be equal to the electromotive force. Combine them, equal to the electromotive force. So we see that, remember, when we talk about the equation, there is not a single equation behind the scene. We will be having plenty algebraic equations, free from derivatives, differential equations involving derivatives, and also integral equations involving integrals. So since we are talking about differential equations, we are interested to get rid of this integral sign. So how we do that? Differentiating this equation does involve integral sign. To get rid of this integral sign, it's an integral of the integrand capital I of t with respect to t. So what we do to kill this effect, to cancel integral, we differentiate it with respect to t. So once we differentiate it, capital R, capital C are being constant, capital I stand for current being function of t. So if you differentiate the first term to the left hand side, so R times d I upon dt, because I is going to be function of t. So di upon dt. In the second term, integral and differential, they will cancel out, and we left with the integrand, the original function. We get the original function back. The fundamental law of calculus, they will kill each other effect. And with the right hand side, differentiated with respect to t. This could also be written as by dividing this equation by capital R, since R and C are constant. So it is going to be di upon dt plus 1 upon RC times I is equal to 1 upon RdE upon dt. Again, this is going to be linear differential equation in the dependent variable I. So pretty much the same equation, just like we have obtained in the first case. So it's the case when we have RC circuit. The first one, RL, RC. Now we move on with LC circuit. So again, pretty much on the same line, we are expecting to involve inductors. Symbolic representation is capital L. The capacitor, symbolic representation is capital C for the capacitance of the capacitor, and electromotive force is a capital. Yes, please.
सर आपकी स्लाइड्स नहीं शो हो रही.
It's there, should be there. Okay, let me do it again. Is it visible now? All right. So, following the previous criterion, we are expecting to involve inductor. The symbolic representation for inductance of an inductor is capital L. Capacitance of a capacitor as a symbolic representation is C, and then the electromotive force capital E. So what we are expecting, the voltage drop across the inductor is that equation we have gone through with the definition and eventually the corresponding expression for capital E. The voltage drop across the capacitor was E equal to 1 upon C integral of I with respect to time t, the variable of integration. And then using Kirchhoff's voltage law, the sum of the drops must be equal to the electromotive force. To combine them, E. So again, we see that yes, it's an integral sign over there. So we are interested to get rid of that. Differentiating this equation with respect to t. So once we differentiate the first term, so it will turn out to be second rate of change of capital I with respect to t from the second term. Integral and differential, they will kill each other effect, and we get the original function back, capital I, by using fundamental theorem of calculus. To the right hand side, differentiated with respect to t, since capital L is going to be constant, so we can differentiate, divide it, this equation by capital L to make things more simple, more composed and compact form of the equation. So it is going to be second order linear differential equation because there is no sign of non-linearity with constant coefficients. So the mathematical model for LC circuit is entirely different in comparison of the previous two models. we have a second order differential equation. Move on to the third one, RLC, where we will be having resistance of a resistor, inductance of an inductor, capacitance of a capacitor, all together. So we are expecting the voltage drop across the resistor, the voltage drop across the inductor, and then the voltage drop across the capacitor. All three equations are going to be utilized, ER, EL, and then EC, by Kirchhoff's voltage law combined together, and then must be equal to the electromotive force. Since we have integral sign over there, again differentiate it to get rid of this integral sign. Derivative to I means the first derivative. Derivative to di upon dt means the second rate of change of capital I. Integral and differential, they will cancel each other. Derivative to E with respect to t. We can also make it more simple. If you divide it by capital L. So because we try to make the coefficient of the first term extreme left as 1. So this is all. I mean, if you don't do that, it's fine. But to make it more elegant, we divide it by capital L on both sides. So if you carefully look into that, we have dependent variable. We have first derivative. We also have a second derivative. The right hand side is going to be non-zero. So we say that it's a second order non-homogeneous because the right hand side is non-zero. Second order because the highest derivative that appears with constant. Coefficient is constant in the second term as well as in the third term to the left, everywhere. So when we have a non-homogeneous higher order differential equation, we know the procedure behind the scene. How do we find the solution? We need to find the general solution of the corresponding homogeneous part by taking the right hand side 0, and then once we look into the right hand side, we will have to find another part of the solution known as particular integral. The combination of them will take us to the general solution of the given non-homogeneous linear differential equation. So we have 4 models behind the scene. RL, RC, LC, and then RLC circuits behind the scene. 2 of them, they will take us to the first order differential equation, and 2 of them, they will be modeled in the form of second order differential equation. So now we look into the practical demonstration by taking a few examples. For example, we have an RL circuit that contain a resistor of resistance 8 ohms, capital R is given as 8, an inductor of inductance 0.5, capital L is equal to 0.5, capital R is equal to 8, constant capital L is equal to 0.5. These are the units, ohms and henries. And a battery of E volts. I mean, it will be given to you as an expression of that. So at time t equal to 0, the current is 0. I mean, this is going to be a condition. And we know that generally what happens, generally at the start of time, we consider it an initial time, t equal to 0. Generally, we take it. Not necessarily, but generally, we assume that t equal to 0 is going to be considered as initial time. Different phenomena are there. where we will be having non-zero time. But in this case, t is equal to 0 means the initial time is a, the current is going to be 0, means it will take us to the initial condition for the starting value of the independent variable. The value of the dependent variable is going to be 0. Since we know that current depends upon t, so I of 0 will be equal to 0. That will make the initial condition. When t is equal to 0, the current will be equal to 0. What are we interested for? We are interested to find the current at any time. And time should be non-zero. Of course, can't be negative value. Surely it will be positive. If a battery of that volts, first option, a battery of that volts is given. I mean, in the first case, capital E will be equal to this one as an expression. For the second case, it will be that. How do we observe that? Based upon the time, the battery, I mean, this is how you will observe the source of energy behind this. All right, since it's an RL circuit, and we know the mathematical model of that. We have gone through that. RL, the first one. So we know the corresponding differential equation for the current, because current stands for the dependent variable in this case, is that one. R is given 8, capital L is given 0.5, and then we will see that E is given. The first part is a, when E is equal to 32 times e raised to power minus 8, and the second case it's a different expression. The product of t and exponential function. So now, if you look into the equation number 32, we know that it's a linear in the dependent variable capital I. So what we need to do, we will have to find the integrating factor. So how do we find the integrating factor? Just like the standard form that we utilized for the linear differential equation dy upon dx, that was dy upon dx plus p of x y equal to q. So that was the expression over there, in the standard form. So p is equal to, in this case, r upon l. And we know how do we find the integrating factor, e raised to power integral p, and then with variable of integration. Over here, the variable of integration is going to be t. So make sure this is our e in this case. So e raised to power integral of p with respect to the variable of integration. So the independent variable is t. So this is all the variable of integration is going to be t. So they are constant values. Could be taken out outside the integral. They will cancel out the integral and differential, and be left with that integrating factor. And we know how do we proceed for the solution. Multiply this equation by the integrating factor. You will see that the left-hand side becomes the exact differential exact differential of the dependent variable together with the integrating factor. If you remember the criterion, the procedure for the solution of linear differential equation, the dependent variable is capital I, the integrating factor we just have obtained e raised to power r upon lt. So to the left hand side, I times e raised to power r lt, and then we take it to the right hand side with negative exponent, and the right hand side is there. Of course, you need to integrate that one because of the differential to the left hand side, taking integral on both sides. So eventually, this is going to be the form of the solution. So a couple of steps you need to perform before you get down with this expression. So I can be obtained by performing integration to this expression. Constant of integration is there. E is known, R is known, capital L is known, so all of them are known. So if you plug in those values, capital R 8 capital L. So the previous differential equation, I mean, if you are interested to see this one, plug in capital R, capital L on both sides. So it will be of this form. And then the solution of this one from here would be of this form. Because we have taken the generalized case in the form of R and L and obtained the solution over here. So if you plug in the value of capital R, the capital L, so it will be something like that. So until now, it will be same in both cases. Either you are going to attempt first or second part. So for example, we are looking for the first part, capital E. So we need to replace E is a function of T, remember? So 32 times e raised to power minus 8t. So plug in E of t 8 times e raised to power minus 8t. So plug in over here. So 2 into 8 is going to be 16. Oh, it was 32, sorry. 32 times 2 will be equal to 64. E raised to power minus 8t, so we can combine them because of the same base. So we left with e raised to power 8t, 64 could be taken outside the integral being constant. Integral of e raised to power 8t, I mean, because the derivative is there, I mean, you need to do that. E raised to power, integral of e raised to power t is going to be e raised to power t, and then the derivative to the exponent in the denominator. So it will be 8 in the denominator. Cancel out with 64, we left with 8. So integral to this expression with respect to t eventually take us to 8 times e raised to power 80 plus constant of integration. You can multiply with this one, combine them in the first term, and combine, multiply it with c as the second term. Now, finally, we are interested to find, or we are interested to get rid of c, the arbitrary constant, the constant of integration. It's current for any time t, but there is an arbitrary value. Won't take you to the particular solution. So what we do, we apply the given condition. What the condition is, again, at time t equal to 0, the current is going to be 0. Initially, of course, when no process is done, when switch is off, then of course t is 0 and the current is going to be 0. So we apply this condition. T is equal to 0. When t is equal to 0, there is no current. Of course, from the above equation, so I will be 0 when t is equal to 0. To the right hand side, e raised to power 0 is 0, e raised to power 0 is 0, so 8 plus c equal to 0. From here, you can get the value of c minus over here. So eventually, I will be equal to 8 times e raised to power minus 8. C is being replaced by minus a. So this is all. We have obtained the current at any time t for an RL circuit. If a circuit is there of this type, so we know the mathematical model, got an idea, and then the procedure to simplify that. Being a mathematician, what we do basically, we take as granted the mathematical model, and then in particular for this particular course, we take as granted the mathematical model, and then we look for the solution based upon the criterion developed based upon a certain type of the differential equation. We look into the solution. So we have seen that the phenomena is a RL circuit is a practical demonstration. We know the mathematical model. Not every time you need to go and then formulate or model that mathematical formulation. We take as granted. It's been done. So for RL circuit, mathematical model is there, and our task is to look into the solution of this one. The solution of this differential equation will take us to the solution of this phenomena. This is how the cycle is there, remember, from the previous lectures. Recall that. From the physical phenomena, and differential equation will take us back to the solution of the phenomena. Phenomena is a differential equation being the mathematical model. Once we find the solution of this differential equation, it will take us back to the solution of this physical phenomena, and that's what we have seen. The current at any time is given by this expression. Find the current in an RC circuit at any time t when the circuit has electromotive force, means capital S times capital R 100, capital C 0.0005, for example, and no charge on the capacitor is there. So you need to go back, look into the mathematical given conditions. Another example for an LC circuit, we are interested to find current at any time when inductance of an inductor is given as 2 henries, capacitance of a capacitor is 0.005, capital E, the electromotive force, 210 times sine of 40, and with certain conditions behind the scene. What are those conditions? Initial conditions are there basically. Initial conditions are there. Current is 0 at equal to 0, and then the time rate of change of current is also equal to 0. So eventually, the answer is going to be that one. Those conditions are basically used to get rid of those arbitrary constants from the solution. Once you get an expression for capital I, you need to apply those conditions. Take the derivative of that solution. One condition is to be implemented on the answer, and the second condition to be implemented on the derivative of the answer, and apply them to get the two arbitrary constants, and eventually the answer will be something like that. Third one, RLC circuit. We are interested to find current in the RLC circuit. Resistance of a resistor is given, capacitance of a capacitor is given, inductance of an inductor L is given, and then the electromotive force is there, 37 sine of 10t. And we have two conditions again. I of 0 equal to 0, I prime of 0 equal to 1. So these are the initial conditions. The difference between initial and boundary conditions is that if all the conditions are subject to only one value of the independent variable, the conditions are known as initial conditions. You see that two conditions are there, but they are subject to only one value of the independent variable, 0. T is equal to 0, T is equal to 0, for one value of the independent variable. So this is how we say that this problem is known as initial value problem, because phenomena is there, mathematical model will be there together with initial conditions. So problem together with initial conditions will take us to the initial value, and eventually the answer will be something like that. All right, so this is all. We got an idea, and I believe that you people must have better understanding in comparison of me about this particular topic, because you do perform experiments in the lab look into those form of circuits. Let me generate a poll for attendance. Beautiful. All right, I generate a poll. Twenty, right? 6th of July, present. No need of this option. So, okay. So battery is going to down. Okay. So the poll has been created for attendance purpose. So this is all. I mean, there are plenty of applications, of course, for differential equations. But we have gone through with a few of them. Depends upon the time constraint. That's what we could look into. So we started off talking about differential equation. Idea is there, foundation is there, basic types of the equations of different order, the criterion, how do we look into the solution, and then eventually we discuss few of the applications. There are plenty, of course, and we cannot cover in this course because of some other aspects to be discussed in this particular course. So next time we will try to look into the Laplace transformation. An idea is it will take us the initial value problem to the algebraic problem. We will look into the solution of algebraic problem, and then the inverse of Laplace will take back to the solution of the given initial value problem. So generally speaking, when we talk about ordinary differential equation, they are going to be initial value problems. Generally, when we talk about partial differential equations, they are going to be boundary value problems. So differential equations will be there with certain conditions, certain initial conditions. So they are going to be initial value problems. So what the objective of Laplace transformation, it will transform the initial value problem into the algebraic form. Much easier to simplify those algebraic equations. Plenty of options are there. So we will find the solution of that algebraic formulation, and then the inverse of Laplace will take back to the solution of the given initial value problem. So this is how we will try to look into the implementation of Laplace transformation. All right, so that's it. If you have any query, short query behind the scene. Our lectures, our files been sent to you. People can take a look at the provided lectures. Okay, I will try to look to generate, upload previous lectures on YouTube. Okay, I will do that, inshallah, in the next couple of days. I don't have an account over there, so let me do that. in the next couple of days, inshallah. All right, then, thank you very much. See you, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.